Close your eyes for a moment and imagine the universe as an immense ocean, dark and endless, with scattered islands of light. These islands are the stars, the galaxies, the beacons of matter adrift across space-time. Even with the fastest engines our imagination allows, the distances between them are daunting. A journey from one island to another would take not years, not centuries, but tens of thousands of years. This immensity is not just inconvenient, it seems insurmountable. And yet, physics asks us a question that feels more like a riddle than a solution. What if there are hidden passages across this ocean, secret bridges that fold the vastness into something traversable? These imagined passages are wormholes, tunnels through space-time that connect places otherwise separated by gulfs too great to cross. Step through one end, and you might emerge light years away in an instant. They are not merely the stuff of science fiction, they emerge naturally from the mathematics of Einstein's general theory of relativity. In 1916, just 1 year after Einstein first published his theory, an Austrian physicist named Ludwig Flamm noticed something peculiar. Relativity did not only predict black holes, the cosmic abysses from which nothing can escape. It also suggested the possibility of their opposites, white holes, fountains of matter and energy erupting outward. Flamm speculated that these two could be linked, forming a kind of bridge across space-time. 2 decades later, Einstein himself, working with Nathan Rosen, explored this geometry. The result was what we now call the Einstein-Rosen bridge, the first mathematical description of a wormhole. To picture this, take a sheet of paper and draw 2 dots far apart. The shortest path is a straight line, but if you fold the paper until the dots touch, suddenly the distance vanishes. A wormhole is like that fold, space-time itself bent so that 2 distant regions touch. It is an extraordinary idea, but like many extraordinary ideas, it comes with caveats. The Einstein-Rosen bridge exists only in theory, and even there it collapses almost instantly. It pinches off before anything, not even light, could pass through. A bridge that vanishes the moment you try to cross it is more a tantalizing mirage than a practical passage, and yet the concept refuses to fade. What if, theorists ask, some exotic form of matter, something with negative energy density, could hold the wormhole open, propping its throat like the ribs of a tent? If such matter exists, then so might stable wormholes. If not, they remain beautiful mathematics and nothing more. The implications, if they could be real, are staggering. Journeys across galaxies in moments. Connections not just between places, but perhaps between times. For if a wormhole links one moment to another, then time itself may not be the barrier we believe. Through wormholes, we might contemplate travel into the past, or glimpses of futures not yet written. But with such possibilities come paradoxes, loops of cause and effect that challenge the very notion of reality. For now, wormholes belong to theory. No telescope has glimpsed one, no particle has betrayed their presence. And yet they are valuable, not because we can step through them, but because they remind us that the universe is stranger than it appears. The equations of relativity whisper of hidden geometries, of unseen architectures within space-time. Wormholes may or may not exist, but the fact that they can exist in principle tells us something profound about the flexibility of the cosmos. Every wormhole story, like every star's story, may also be our story, because in asking whether shortcuts exist, we are really asking about the limits of our journey and whether those limits are final. Perhaps one day, with deeper understanding, we will know whether the universe hides secret roads. Until then, wormholes remain both science and poetry, symbols of our desire to explore, to connect, to transcend the boundaries that surround us. And so, our journey begins with the mystery of cosmic shortcuts, the tantalizing thought that across the dark ocean of the cosmos, there may be hidden bridges waiting to be found. And while you're here, tell us in the comments where in the world you are and what time it is beneath your sky. If you're enjoying this journey, please consider subscribing so you can join us again for more adventures through the cosmos. From the dream of hidden shortcuts We move now to the dream of cosmic shortcuts. This next part brings us closer to their first mathematical form, the Einstein-Rosen bridge. It is here that the abstract beauty of relativity begins to suggest that the fabric of the universe may contain tunnels, concealed corridors hidden from ordinary view. When Einstein and Nathan Rosen examined the equations of general relativity in 1935, they found something remarkable. Black holes, which until then were considered mathematical curiosities, contained within their description a strange doubling of space. If one solved the equations carefully, another region of spacetime appeared, one that seemed to mirror our own. The connection between these two regions became known as the Einstein-Rosen bridge. The bridge is unlike the images of wormholes we often see in popular imagination. It is not a convenient tunnel with smooth walls and glowing edges, but a structure that exists within the mathematics of curved spacetime. Imagine spacetime as a kind of rubber sheet stretched taut. A black hole is like a deep pit carved into that sheet. The Einstein-Rosen bridge suggests that beneath that pit lies not a singular ending, but a throat leading to another pit that opens elsewhere, perhaps into another universe entirely. At first glance, it sounds like a portal, a cosmic underpass across light years. But the reality is far less forgiving. The Einstein-Rosen bridge is unstable. The moment anything tries to pass through, it collapses. Like a soap bubble pierced by a finger, it cannot bear disturbance. Even light, the gentlest traveller of the cosmos, cannot make the crossing before the throat pinches shut. This fragility is not a flaw in the mathematics. It is a feature of it. The equations insist that gravity, while it can carve tunnels, is also relentless in closing them. It is as though the universe tolerates the idea of bridges in principle, but refuses to allow them in practice. And yet Tot embraced the notion of traversable wormholes, but the seeds were planted and others would nurture them in decades to come. To understand the Einstein-Rosen bridge is to see how deeply relativity reshaped our view of reality. Space and time are not static arenas, as Newton imagined, but elastic. They can twist, bend, stretch, and, in theory, join together in hidden passages. We may never walk across such a bridge, but knowing it exists within the mathematics is enough to remind us that the universe is not bound by our intuitions. And there is a metaphor here too. We often imagine obstacles as impassable, distances as insurmountable, yet sometimes unseen connections link what seems impossibly far apart. The Einstein-Rosen bridge may never serve as a highway across galaxies, but as an idea it bridges the gap between what we know and what we can only dream. Every great journey begins with such bridges, fragile, fleeting, but powerful enough to guide us onward. From here, our path leads to the question that haunts wormhole theory. Could there be a way to stabilize such passages, to prevent them from collapsing? Could there exist a kind of matter exotic enough to resist the pinch of gravity? That question will take us into this next part, where physics edges into the strange realm of exotic matter, negative energy, and the possibility of holding a wormhole throat open long enough for a traveller to pass through. This next part, exotic matter and stability. The Einstein-Rosen bridge showed us that wormholes can exist in principle, but it also revealed their fatal flaw. They collapse the instant they form. To cross one would be like stepping onto a bridge that vanishes beneath your feet. And so theorists began to ask, could such a structure be stabilized? Could the throat of a wormhole remain open long enough for matter or even light to pass through? The answer, if it exists, lies in the strange realm of exotic matter. In ordinary physics, mass and energy curve space-time in a way that pulls inward. Gravity is attractive, it gathers, it constricts. To keep a wormhole open, you would need the opposite, something that pushes outward, that resists collapse. In the equations of relativity, this requires negative energy density. Substances so alien, they have no counterpart in our everyday experience. Exotic matter is not merely science fiction. In quantum physics, The vacuum itself is not empty, but alive with fluctuations, pairs of particles and antiparticles flashing into existence and vanishing in instants. In certain configurations, these fluctuations can create regions where the energy density is effectively negative. The Casimir effect, discovered in 1948, is one such case. Place two conducting plates very close together, and the quantum vacuum between them has less energy than the space outside. It is as though the plates squeeze the fabric of the vacuum, leaving behind a faint but measurable negative pressure. Could such negative energy be harnessed to support a wormhole? In theory, yes. Exotic matter could act like the scaffolding of a tunnel, preventing gravity from crushing its walls. Without it, the wormhole throat pinches shut. With it, the passage might stay open, but the quantities required are immense. The Casimir effect produces only the tiniest flicker of negative energy. Scaling this up to cosmic proportions would demand a mastery of quantum fields far beyond our present capabilities. Yet the equations do not forbid it. That is enough to keep the idea alive. If exotic matter can exist in large quantities, wormholes could be traversable. They could allow not only the transmission of light, but the passage of travelers. Journeys across galaxies in seconds would no longer be fantasy but physics. This possibility raises profound questions. If wormholes are stabilized by exotic matter, what would such matter look like? Could it be created in particle accelerators? Could it arise naturally in the cosmos, perhaps in regions where quantum fields are stretched by inflation in the early universe? And if so, might wormholes already exist, hidden somewhere among the galaxies, their throats supported by physics stranger than anything we know? But the universe, for all its openness to wonder, remains strict. Exotic matter is not something we can summon at will. Its existence is fragile, fleeting, confined to the smallest scales. We have no evidence that nature has ever created it in abundance, and so wormholes remain, for now, on the border between the possible and the impossible. Still, the pursuit matters. Even if exotic matter is forever beyond our reach, its role in the equations teaches us something vital, that the universe does not close the door entirely. Relativity does not forbid wormholes. Quantum physics even offers a mechanism, however faint, to hold them open. The cosmos whispers that shortcuts might be possible, if only we could find the right key. This is the poetry of science. It shows us paths not yet walked, bridges not yet built. Exotic matter may prove to be a mirage, or it may one day be the cornerstone of interstellar travel. Either way, it deepens our sense of what is possible. As we leave this chapter, the question grows sharper. If exotic matter could stabilize wormholes, then the door opens not only to distant travel, but to time itself. For wormholes, once made traversable, are not limited to space alone. They can bend chronology, linking not only places but moments. That astonishing possibility is where our journey turns next. This next part, wormholes and time travel. The possibility of a wormhole held open by exotic matter leads to one of the most extraordinary questions in physics. Could such a passage not only connect distant points in space, but also carry us across time itself? To even whisper this idea is to push at the boundaries of science and philosophy, for space and time are inseparably bound together in the fabric of spacetime. To warp one is to inevitably bend the other. Imagine, then, a traversable wormhole with two mouths. One near Earth, the other carried aboard a spaceship. The craft accelerates to near-light speed, experiences time dilation, and later returns. From the perspective of relativity, less time has passed for the mouth that travelled than for the one left behind. Yet both are still part of the same wormhole. Step into the stationary mouth, and you might emerge not only in another location, but also in another time. A shortcut through the cosmos becomes, in principle, a shortcut through chronology itself. The mathematics is sound. Kip Thorne, Michael Morris, and Ulvi Yurtsever demonstrated in 1988 that wormholes, if stabilized, could act as time machines. Carl Sagan had approached Thorne while writing his novel, Contact. asking for a scientifically plausible method of interstellar travel. Thorne's answer, wormholes, quickly spiraled into the realization that they also bent chronology. In theory, such a device could allow us to visit the distant past or glimpse futures not yet written. But physics is never so generous without a price. Time travel through wormholes confronts us with paradoxes that unsettle our understanding of cause and effect. Consider the famous grandfather paradox. A traveller journeys back and prevents their own birth. How then could they have embarked on the journey in the first place? The logic twists in circles. Igor Novikov proposed one resolution: the principle of self-consistency. Events involving time travel must be consistent with history. You may interact with the past, but only in ways that preserve the future that already exists. Quantum mechanics hints at another possibility. Perhaps traveling through time does not alter one fixed timeline, but instead shifts the traveler into a branching universe. Each choice spawns a new world, and paradoxes dissolve in the endless proliferation of realities. In this view, wormholes might not only be portals through spacetime, but gateways to parallel histories. Whether this reflects physical truth or is merely a mathematical dream remains uncertain, but it shows how far the idea stretches our imagination. Even without paradoxes, the practical obstacles are vast. Stabilizing a wormhole demands immense quantities of exotic matter, negative energy densities far beyond what any technology can summon. The engineering challenge is beyond imagination, yet the equations do not forbid it, and that, perhaps, is the most important point. Relativity allows for wormhole time machines in principle, and that means time itself is not as rigid as our senses suggest. There is a philosophical weight to this as well. If wormholes can reach across time, what does that say about the nature of free will, of destiny, of the arrow of time? Perhaps the universe is not a single flowing river but a landscape, and our journey through it is just one possible path among many. Perhaps time is not something that moves forward, but something we move through, like travelers crossing valleys and mountains. It is unlikely that humanity will ever build a wormhole time machine, but the act of imagining it has already transformed our understanding of reality. It reminds us that time is not absolute, that our everyday experience of minutes and hours is but a local truth. In the deep structure of the cosmos, time can bend, stretch, and, just possibly, loop back on itself. Every wormhole's story is also our story. In thinking about time machines, we glimpse our own longing to rewrite, to revisit, to reconnect with what has passed and what may yet come. Whether wormholes ever allow it or not, the very possibility reminds us that reality is more mysterious, more elastic, and far more extraordinary than it appears. And so, as we leave this chapter, we turn from speculation back to foundations. If wormholes can bend space and time, then the true challenge is to understand the rules of energy and the restless quantum vacuum that fills all things. For in that vacuum may lie the secret of whether such roads through time can ever remain open. This next part, energy conditions and the quantum vacuum. To see whether wormholes could ever remain open, physicists must confront the foundations of relativity itself, the assumptions known as energy conditions. These conditions are not equations in the usual sense, but guiding principles about how matter and energy behave. They say that energy densities are positive, that gravity is attractive, and that space-time curves in ways that match our everyday experience. Without them, Einstein's equations of general relativity become wild and unruly, admitting solution. This is where wormholes begin to push the limits. A traversable wormhole, held open long enough for light or matter to pass through, requires something profoundly strange: negative energy density. It is as though space-time demanded an ingredient entirely outside the menu of ordinary matter. Such matter would not simply resist collapse, it would actively push against it, creating an anti-gravity effect. Without this, the throat of a wormhole slams shut faster than even a photon can escape. At first glance, the requirement seems absurd. Where in the universe could such negative energy exist? But here, quantum mechanics enters the stage with its unpredictable flair. The vacuum of space, once thought empty, is restless and alive with fluctuations. Tiny pairs of particles and antiparticles flicker into being, then annihilate in fractions of a second. These ephemeral dances mean that the vacuum has structure, that it can never truly be nothing. In 1948, the Dutch physicist Hendrik Casimir demonstrated a striking consequence of this quantum restlessness. Place two metal plates very close together, and the vacuum between them has fewer modes of fluctuation than the vacuum outside. The imbalance creates a pressure that pushes the plates together. This Casimir effect can be measured in laboratories, and the key point is that, inside the gap, the energy density is effectively negative compared to the surrounding space. If negative energy exists in small quantities, might it exist in larger ones? Could the strange physics of the quantum vacuum provide the scaffolding to prop open a wormhole throat? The mathematics suggest it is possible. A wormhole supported by such exotic energy would not collapse immediately. Instead, its walls would be held apart by the vacuum's own defiance of classical rules. But scaling up is another matter. The Casimir effect produces forces so tiny that they only shift delicate instruments. To support a wormhole, one would need astronomical amounts of negative energy, quantities that dwarf anything we can produce. The gulf between laboratory measurements and cosmic engineering is immense, like trying to build a cathedral out of soap bubbles. Still, the principle is there. Nature allows it. And so the energy conditions, once seen as inviolable, begin to look less absolute. They are guidelines, not commandments. In the classical world, matter behaves with reassuring consistency. In the quantum world, the rules blur, and what once seemed impossible flickers into possibility. This does not mean traversable wormholes exist, but it means physics cannot rule them out entirely. There is something profoundly beautiful in this. Science often advances by loosening boundaries, by discovering that assumptions thought to be universal are merely local. Wormholes force us to reconsider the very idea of energy and of the vacuum itself. The emptiness between the stars may not be barren at all. It may contain the seeds of the strangest structures imaginable. Every wormhole's story is also our story. For in confronting the limits of energy conditions, we are reminded that the universe is not bound by human common sense. It whispers that reality is larger, subtler, and more flexible than we think. Wormholes may never open before us, but the fact that the equations leave a crack in the door is enough to sustain wonder. And so, from the restless vacuum, our journey continues. If the quantum froth of space itself can sustain wormholes, then perhaps they are not just theoretical curiosities, but natural features of the universe. Could they appear spontaneously, hidden within the fabric of space-time? Could they be connected not only to distant stars, but to the deepest mysteries of quantum gravity? These questions lead us onward into the next chapter of our story. This next part, traversable wormholes in theory. If wormholes exist only as collapsing bridges, they remain tantalizing but useless. To pass through, even for a flash, would be impossible. But in 1988, Kip Thorne and Michael Morris asked a bold question. Could the mathematics of relativity describe a wormhole that was not a fleeting mirage, but a traversable tunnel, a safe passage through space-time itself? Their answer was yes, at least in principle. By carefully manipulating Einstein's equations, they described a space-time containing a wormhole with a throat wide enough and stable enough for a traveller to cross. The traveller would not be torn apart by tidal forces, nor trapped by event horizons, nor crushed by infinite densities. This was a wormhole you could walk through, or fly a spaceship through, and return with a story to tell. The cost, as always, was exotic matter. To hold open the throat, negative energy density was required, something capable of resisting collapse. Thorne and Morris did not pretend this was practical. They knew such matter was speculative, perhaps impossible. But the genius of their work lay in showing that relativity itself imposed no further obstacle. If exotic matter could be found, then traversable wormholes could exist without breaking the known laws of physics. This was a profound shift. Wormholes were no longer mere curiosities hiding inside black hole mathematics. They were candidates for real, physical structures, at least as real as any solution of Einstein's equations. Thorne, already celebrated for his work on gravitational waves, became something more, a physicist willing to bridge the gulf between rigorous mathematics and daring imagination. His collaboration with science fiction and his willingness to dignify speculative questions with serious answers opened the door for a new kind of dialogue between art and science. The Morris Thorne wormhole soon became a thought experiment used in classrooms, in conferences, in papers testing the limits of relativity. Students could calculate what stresses a traveller might feel, what paths light would take, how clocks would tick differently inside the tunnel. In doing so, they were not building wormholes but probing the edges of possibility, mapping where reality ended and where dreams began. And here lies one of the greatest gifts of theoretical physics, the ability to chart worlds that may never exist, yet that reveal the logic of the cosmos. Traversable wormholes taught us that space-time itself is more permissive than we once thought. It will allow shortcuts, provided we find the right ingredients. The universe, it seems, is not opposed to our ambitions. It simply sets conditions we do not yet know how to meet. There is a metaphor here, as there so often is. Sometimes the barriers in our lives are not walls but thresholds. With the right support, with the right structures, a way through can be found. Wormholes remind us that nature too has thresholds, riddles waiting for solutions. Every wormhole's story is also our story. In imagining traversable wormholes, we glimpse our own desire to transcend limits, to reach the unreachable, to explore the uncharted. Even if we never build one, the act of contemplating them enlarges us. And so we leave this chapter not with blueprints but with possibilities. If wormholes can be traversable, then perhaps they exist already, born in the violence of the early universe, hidden among the galaxies, waiting to be discovered. But if they do, they belong not only to relativity, but to the realm where relativity and quantum mechanics meet. And that is where our journey now turns, to quantum gravity, and to the idea that wormholes may be stitched into the very fabric of the quantum world itself. This next part, wormholes in quantum gravity. General relativity describes wormholes with elegance, but it is incomplete. It bends space-time smoothly, endlessly, like a sheet of rubber. Yet the universe, at its smallest scales, is not smooth. It is granular, restless, flickering with uncertainty. To truly understand whether wormholes exist and whether they could endure, we must step into the uncharted territory where gravity meets quantum mechanics, the long-sought theory of quantum gravity. At the Planck scale, distances a trillion times smaller than an atom. Space-time itself is thought to resemble a froth, a boiling foam of geometry. In this microscopic seething, tiny wormholes may constantly flicker in and out of existence, tunnels opening and closing in less than an instant. They're too small for light, too unstable for matter, but their presence could be part of the very architecture of the cosmos. This is sometimes called quantum foam, and if it is real, wormholes are not exotic. The dream of quantum gravity is to unify two of physics' greatest triumphs, Einstein's general relativity, with its smooth curves of space-time, and quantum mechanics, with its probabilistic fields and particles. String theory is one contender, suggesting that the fabric of space-time arises from vibrating strings in higher dimensions. Loop quantum gravity is another, proposing that space itself is woven from discrete loops. In both visions, wormholes appear naturally as features of the geometry, the connection. One of the most intriguing ideas of recent years is the ER equals EPR conjecture. Proposed by Juan Maldacena and Leonard Susskind, it suggests that every pair of entangled particles is connected by a tiny wormhole. Entanglement is the strange property of quantum mechanics where two particles, no matter how far apart, remain linked. Measure one, and the other responds instantly. ER equals EPR proposes that this link is not just abstract but geometric, that spacetime itself provides the connection in the form of a EM. If this is true, then wormholes are not rare. They are everywhere, threading through the universe at microscopic scales, binding particles, weaving together the fabric. This connection between quantum theory and spacetime could resolve another mystery: the fate of information in black holes. If wormholes are the conduit, and here too is a metaphor for us. We think of ourselves as separate, isolated, alone in the vastness of the cosmos. But what if we are all entangled? What if we are all connected, not by visible threads, but by the hidden fabric of the universe itself? Wormholes, real or imagined, remind us that distance may be an illusion, and that separation is never complete. Every wormhole story is also our story. At the human scale, we too long for connections across distance, for unseen bridges that bind. As we leave this chapter, we recognize that wormholes may not be engineering projects waiting to be built, but natural phenomena already humming beneath the surface of reality. If so, then the universe is stranger and more deeply connected than we have ever imagined. And so our journey continues, beyond the smallest scales to the grandest speculation of all. What if wormholes not only connect places within our universe, but bridge entire universes in the multiverse itself? This next part, wormholes and the multiverse. What if wormholes did not merely connect two distant regions of our universe, but stretched further still, linking entirely separate universes? To ask such a question is to step beyond physics as we know it, into the speculative territory where science brushes against philosophy. Yet it is not without foundation. For if the cosmos itself may be larger than what we see, then perhaps wormholes are the bridges that bind its hidden realms. The idea of the multiverse arises naturally from our attempts to explain the universe's earliest moments. According to inflationary cosmology, the Big Bang was not a singular explosion, but a rapid expansion driven by a field of energy. In many models, this expansion does not end everywhere at once. Pockets of space stop inflating, forming bubble universes, while inflation continues elsewhere. Our universe may be one such bubble among countless others. If this picture is true, then the multiverse is a vast cosmic foam, with universes like ours floating side by side, separated by gulfs we cannot cross. But if wormholes exist, they may offer a thread through the foam, a tunnel that links one bubble to another. The physics of such connections is uncertain, but the mathematics does not forbid them. In fact, some solutions to Einstein's equations describe wormholes that connect universes which otherwise have no contact. To step through such a wormhole would be to leave not just Earth, not just the Milky Way, but our entire reality. On the other side might lie a universe with different laws, different particles, perhaps even different notions of time. It is a vision almost impossible to grasp. Other realities, unreachable by any normal means, made accessible by a tunnel carved into the very geometry of existence. For physicists, the question is not only whether such wormholes exist, but what they would mean for conservation laws, for energy, for causality itself. Would information leak from one cosmos into another, altering its history? Would travelers find themselves annihilated, their atoms unable to hold together in alien physics? Or might the laws of nature conspire to keep such journeys forever forbidden? And yet, speculation has value. It forces us to confront the limits of our knowledge, to test our theories against the broadest canvas imaginable. The multiverse may be beyond proof, at least with our current tools. But wormholes provide a framework for thinking about it, for asking how universes might be connected, and what universe truly means. Every wormhole story is also our story. In imagining bridges between universes, we reveal our own longing to transcend boundaries, not just the distances of space, but the limits of imagination. To think of other universes is to think of other possibilities, other versions of existence. It reminds us that reality may be larger, stranger, and richer than we dare to assume. And here is a quiet irony. We may never know if wormholes to other universes exist, and yet by imagining them, we expand our own universe of thought. In this way, the act of speculation becomes a journey in itself. As we close this chapter, let us carry the thought that wormholes may not only link stars and galaxies, but entire realities. And if that is so, then our universe is not an island, but part of an endless archipelago of worlds. The question that lingers is not whether we will ever cross to another bubble, but what such a crossing would mean for our understanding of existence. And so, we turn to imagination, not the imagination of physicists alone, but of storytellers, artists, and dreamers who have carried wormholes further still. For while science reaches cautiously into the multiverse, popular imagination has long leapt through wormholes with abandon. And it is to that realm of wonder and creativity that we now travel. This next part, wormholes in popular imagination. Science is often the art of restraint, of carefully drawing only the conclusions justified by evidence. But imagination knows no such boundaries, and when it comes to wormholes, the human imagination has not only leapt ahead, it has shaped the very way science speaks about them. From the earliest days of speculative fiction, wormholes have been the portals of dreams. They are gateways to distant galaxies, shortcuts across impossible distances, and doors into other times. In novels and films, wormholes are not abstract equations, but glowing arches, spinning vortices, shimmering tunnels lined with light. They are the very embodiment of our yearning to travel, to discover, to connect. One of the most enduring examples is the Stargate of science fiction, a device that collapses distance and allows explorers to step instantly into alien worlds. In these visions, wormholes are domesticated. They are not fragile or unstable, but tools to be harnessed, bridges in an interstellar highway. And though the physics is embellished, the spirit of the idea remains faithful to relativity itself, that space and time are pliable, that shortcuts through the cosmos may exist. In cinema, wormholes have become cultural touchstones. Films like Contact and Interstellar present wormholes not only as mechanisms of travel, but as metaphors. In Interstellar, the wormhole is a gift, an opportunity for humanity to survive. It is also a symbol of love, of connection across time and distance. Kip Thorne, the physicist who helped formalize traversable wormholes, was an advisor on the film, ensuring that even the fictional portrayal carried the flavor of real science. In this way, the boundary between science and storytelling blurs, each feeding the other, weaving equations and imagination into a single, shared vision of the cosmos. Wormholes in imagination also reflect our anxieties. They are sometimes depicted as traps, unstable passages that collapse and strand travelers forever. They remind us that shortcuts may be dangerous, that tampering with the deep structure of reality carries risks. Even in their fictional form, wormholes mirror our ambivalence toward technology, the balance of hope and fear that comes with every great discovery. What is striking is how fiction and science have danced together in this story. The term wormhole itself owes its popularity as much to popular culture as to physics. Writers embraced it, expanded it, and in turn inspired new generations of scientists to wonder. A student's question about wormholes led Kip Thorne to develop the Morris-Thorne model, proof that ideas seeded in imagination can bear fruit in rigorous theory. Every wormhole story is also our story. The ones in novels and films may not obey Einstein's equations, but they obey something else: the human spirit's refusal to accept limits. We tell stories of wormholes because they echo our desire to reunite with lost loved ones, to cross the barriers of time, to explore what lies beyond the horizon. In this sense, the wormhole is not only a scientific hypothesis, but also a myth of modern times. It is the heir to the magic portals of folklore, the enchanted doorways and hidden paths of ancient storytelling. Where once we imagined stepping into fairy realms or divine kingdoms, today we imagine stepping into another galaxy. The physics has changed, but the longing is the same. And here is where science and imagination meet most fruitfully. For science is not only about what we know, but about what we can conceive. Fiction expands our palette of possibilities. It keeps alive the sense that the universe may hold wonders beyond our present grasp. Wormholes, whether real or not, teach us to keep asking questions, to remain open to what seems impossible. As we close this chapter, we step from imagination back into physics. For while stories give wormholes form and colour, black holes give them gravity. And some physicists wonder whether the two phenomena are entwined, that behind the veil of a black hole might lie a passageway, a wormhole hidden in shadow. That is where we now turn. The possible kinship between wormholes and black holes, and what it might mean for our understanding of the cosmos. This next part, wormholes and black holes. Black holes and wormholes are often spoken of in the same breath, as if they are cousins born from the same equations, and in a sense they are. Both emerge from Einstein's general theory of relativity, and both reveal how spacetime can be twisted to extremes. Yet while black holes are now established astrophysical realities, wormholes remain hypothetical, their existence uncertain. The question is whether the two might in fact be connected. A black hole is formed when a massive star collapses, crushing matter so tightly that gravity overwhelms all other forces. At its heart lies a singularity, a point where our equations falter, where density is infinite and space-time curves without limit. Around this singularity is the event horizon, the boundary beyond which nothing can escape, not even light. To us it appears as darkness itself, a sphere of absence. But the mathematics of relativity admits another possibility. If a singularity does not end in a dead end, but in a bridge, then a black hole might connect to another region of space-time. Early solutions to Einstein's equations, such as the maximally extended Schwarzschild geometry, hinted at such structures. These theoretical constructs resembled tunnels, wormholes, linking our universe to another, or to a distant part of our own. Penrose diagrams, those elegant maps of space-time, even show how such connections might look. In these diagrams, black holes are not isolated pits but gateways, their interiors extending to other regions. The image is compelling. Perhaps every black hole is a hidden doorway, its darkness concealing a passage beyond. And yet, reality seems less generous. Most physicists believe that real black holes are too unstable to harbour wormholes. Quantum effects near the singularity, combined with the violence of collapse, likely close off any such pathways. The mathematics may allow them, but nature does not seem to indulge them. Still, the connection between wormholes and black holes is valuable. It teaches us that the universe's most extreme objects are not just curiosities, but laboratories for our theories. By studying black holes, by listening to their gravitational waves, we test the same mathematics that describes wormholes. Each ripple in space-time carries hints of what relativity permits and what it forbids. There is another way in which the two are linked. Wormholes, if they exist, would require exotic matter to remain open. Black holes, by contrast, are formed by ordinary matter collapsing under its own weight. They are opposites. One demands an ingredient we do not know how to find. The other is born from the stars we see every night. And yet both remind us that space-time is dynamic, not fixed. The fabric of reality can collapse or it can connect. Every wormhole's story is also our story. Black holes, once thought to be purely destructive, are now seen as engines of galaxies, shaping the cosmos with their gravity. Wormholes, still only in equations and stories, represent the possibility of connection. One teaches us about endings, the other about possibilities. Together they form a mirror of human experience, the inevitability of limits, and the dream of transcending them. And so, as we leave this chapter, we recognize that wormholes and black holes may never be twins, but they are kin. To study one is to glimpse the other. To imagine a wormhole hidden within a black hole is to push relativity to its edge, to let the mathematics guide us into realms we may never see. Our next step takes us deeper still, not into the mathematics of bridges, but into the paradoxes they create. For if wormholes allow time travel, then they do more than bend space. They bend causality itself, and that is a mystery every bit as troubling as the singularity inside a black hole. This next part, challenges and paradoxes. Every great idea in physics comes with consequences, and wormholes, perhaps more than any other idea, force us to confront contradictions. They offer breathtaking possibilities, instant travel, time shifts, even crossings into other universes. But they also open doors to paradoxes that seem to threaten the very logic of reality. The most famous of these is the grandfather paradox. Imagine travelling through a wormhole into the past, arriving before your grandparents ever met. If you were to prevent their meeting, your own birth would never occur. But then, who was it that travelled back in the first place? The paradox spirals in on itself, a loop of causality that seems impossible to resolve. Physicists have long wrestled with such problems. Kip Thorne and Igor Novikov proposed what they called the self-consistency principle, that the universe somehow forbids paradoxes. According to this view, you may indeed travel through time, but only in ways that preserve consistency. If you go back, your actions were always part of history. You cannot undo your own existence because the universe ensures that the story fits together without contradiction. But is this principle law, or assumption? Could the universe truly conspire to avoid paradoxes, reshaping events so that time remains intact? Or is it simply our attempt to make peace with equations that otherwise seem to permit the impossible? Other paradoxes emerge too. Consider the information paradox. If wormholes allow time travel, could they create causal loops where knowledge or objects appear without origin? A book might be passed back in time through a wormhole, copied and returned forward again, yet no one ever wrote it. The information simply exists, cycling endlessly. Such loops trouble our understanding of causality, suggesting that effect might create cause rather than the other way around. Even without time travel, wormholes pose challenges. If they exist, do they allow signals to move faster than light? Relativity insists that nothing outruns light in normal space. But if wormholes permit shortcuts, then information could traverse them and arrive before light travelling the long way around. Would this violate causality? Or does relativity itself allow such exceptions, provided the geometry is right? And then there is the question of stability. Even if exotic matter could hold a wormhole open, would it remain open in the face of quantum fluctuations? Some theorists argue that radiation, travelling through the wormhole, would build up uncontrollably, collapsing it in an instant. In this view, the universe protects itself, sealing the shortcut before paradoxes can arise. Every wormhole story is also our story. These paradoxes mirror our own struggles with freedom and fate. We long to change the past, to rewrite regrets, to step outside the flow of time. Yet perhaps the universe tells us what we already suspect, that our lives, like its history, are self-consistent, that the choices we make, the paths we take, cannot be untangled from the fabric of reality. And yet, paradoxes also point the way forward. They reveal the boundaries where our theories break down, where relativity and quantum mechanics clash. By exploring these puzzles, physicists are not chasing impossibilities but testing the strength of our understanding. Each paradox is a signpost, pointing toward the deeper theory still to be found. As we close this chapter, we carry with us the recognition that wormholes are not just curiosities of mathematics. They are challenges to causality, to information, to the very logic of existence. To imagine passing through one is to imagine stepping into a realm where effect might precede cause, where stories loop without beginning or end. And so, our journey turns from paradox to pursuit. For if wormholes exist, how would we ever know? What signs would they leave in the sky? What fingerprints on the cosmos might betray their presence? That is the question we now follow: how to search for wormholes in the vastness of the universe. This next part, searching for signs. If wormholes exist, they may not announce themselves with glowing tunnels of light or swirling cosmic gateways. The universe is quieter than our stories, more subtle in the way it hides its secrets, and so the question becomes, if there are wormholes out there, how could we ever hope to detect them? Physicists begin with the language of gravity. Wormholes, like any massive structure, would bend space-time. Light passing near them would not travel in straight lines, but curve. This effect, gravitational lensing, is already observed in galaxies and clusters, which magnify and distort the light from more distant objects. A wormhole, if it bent light in an unusual way, might reveal itself through patterns of lensing that no black hole or star could produce. Imagine a star orbiting something invisible. If its path deviated from what we would expect around a black hole, astronomers might suspect the presence of a wormhole. Or imagine two stars apparently connected by nothing, yet their light arriving with a strange delay, as though it had passed through a hidden tunnel. Such subtle signatures are the kind of clues astrophysicists search for. There are even suggestions that wormholes, if they exist at galactic scales, could act as conduits for cosmic rays or high-energy particles. If a burst of radiation appeared from nowhere, with no nearby astrophysical source, could it be a message carried through a hidden shortcut in space-time? Gravitational waves, too, offer a new way to listen. When black holes collide, they send ripples across the cosmos, which observatories like LIGO and Virgo now detect. If wormholes existed, their dynamics might create distinctive echoes, reverberations in the waves that differ from the signature of black holes. Some researchers are already combing the data, searching for patterns that could hint at something stranger than collapse. And yet, the search is fraught with difficulty. Wormholes, if real, may be rare, unstable, or microscopic. They may flicker open and shut in the quantum foam, leaving no trace for our instruments to catch. Or they may exist in regions of the universe too distant for us ever to observe. The silence of the cosmos may not be proof of their absence, but only of their elusiveness. Every wormhole's story is also our story. Our search for them mirrors our search for meaning. Patient, persistent, aware that the answers may always lie just beyond our grasp. To look for wormholes is to look for possibilities, for evidence that the universe is richer than it appears. Even if the search never succeeds, it is not wasted. For in designing the methods, in building instruments to detect the faintest ripples of gravity, in teaching ourselves to see the universe with new eyes, we expand our understanding. The pursuit of wormholes strengthens the science of black holes, of galaxies, of space-time itself. It teaches us to push further, to demand more of our curiosity. And there is something poetic in this. Wormholes may be silent, invisible, evasive, and yet in chasing them, we find ourselves sharpening the very tools that reveal the universe's most profound truths. As we close this chapter, we must admit, we do not know if wormholes exist. We may never know, but in searching for them, we embody something essential about humanity. We are explorers not only of oceans and continents, but of ideas, of possibilities. We look into the night sky not to confirm what we already know, but to wonder what might still be hidden. And so, our journey carries us forward, not into the skies, but into reflection. For wormholes do not only challenge our instruments, they challenge our philosophy. They make us ask what it means for two places to be connected, what it means for reality itself to be stitched together. That is the path we now take, into the philosophical implications of wormholes and the meanings they hold for us. This next part, the philosophical implications. To speak of wormholes is to speak not only of physics but of philosophy. For these imagined tunnels through space-time raise questions that extend beyond mathematics into the realm of meaning. What does it mean for two distant places to be connected? What does it mean for time itself to loop or bend? At its core, the idea of a wormhole asks us to reconsider the very fabric of existence. We are accustomed to thinking of space as an expanse, a stage upon which events unfold. Time, in turn, seems like. For philosophers, this raises questions of causality and identity. If wormholes allow time travel, what becomes of free will? If our future can influence our past, then are we truly agents of choice, or simply actors following a script written by space-time itself? And if 2 points in space are connected, does distance retain meaning? Is here and there still a distinction? Or does the wormhole reveal that such boundaries are illusions? In another sense, wormholes echo ancient human myths. Across cultures, stories abound of hidden pathways, enchanted doorways, and sacred bridges that link worlds. From the Norse Bifrost to the tunnels of Greek underworld myth, humanity has long dreamed of connections that transcend ordinary limits. Wormholes, in their way, are the scientific heirs of these myths. Not magical, but mathematical, yet carrying the same symbolic weight. Every wormhole's story is also our story. For when we imagine them, we reveal our own longing for shortcuts, for reunions across time, for ways to escape the constraints of mortality. Wormholes mirror our deepest desires, to undo regrets, to see loved ones again, to journey beyond horizons. Whether or not they exist in nature, they exist in us, in the architecture of our imagination. There is also the question of knowledge. If wormholes connect distant places, then the universe is not a disconnected patchwork, but a whole bound together by hidden threads. This invites us to think of reality not as a collection of separate parts, but as a unified web. It suggests that our separations between galaxies, between people, even between moments in time, may be less absolute than they appear. In the philosophy of science, wormholes remind us of the delicate boundary between speculation and understanding. They are solutions to equations, but equations are not the universe itself. They are maps, not the territory. To mistake the two is to lose sight of what physics is, not certainty, but a dialogue with nature, a conversation where each answer opens more questions. And yet this is precisely the beauty. Wormholes teach us humility. They remind us that our understanding of reality is provisional, incomplete. They leave open the possibility that the cosmos is stranger than we can yet conceive. As we step from philosophy back into physics, we see that wormholes sit at the frontier of knowledge. They are not confirmed, perhaps not real, but they are meaningful. They teach us about the flexibility of space-time, about the reach of imagination, about the interplay of science and myth. And so, as we leave this chapter, we recognize that wormholes are not only tunnels through space-time, but mirrors held up to ourselves. They show us our yearning for connection, our unease with limits, our hunger for meaning. Whether real or not, they are part of the human story, the story of beings who look to the stars and wonder what lies beyond. Next, we turn from philosophy to the frontier of science itself. What lies ahead in wormhole research? What tools might reveal new clues, and how might our theories evolve? That is the path we now follow, toward the future of wormhole physics. This next part, the future of wormhole research. Speculation is only the beginning. For wormholes to move from imagination into science, we must ask, how might we test the idea? What clues might the universe offer? And what paths might the next century of research take toward uncovering these hidden connections in space-time? Today, wormhole physics rests on theory, on the mathematics of relativity and quantum field theory. But theory is not idle. It shapes experiments, directs telescopes, and suggests where to look. The first frontier is astrophysics. With instruments like the Event Horizon Telescope, which captured the first image of a black hole's shadow, we may one day detect anomalies that hint at wormholes, Subtle distortions in gravitational lensing or echoes in gravitational waves could provide the first indirect evidence. The second frontier is quantum theory. As we probe the vacuum with greater precision, we uncover the strange behavior of negative energy and quantum entanglement. If wormholes are supported by exotic matter, then advances in quantum optics and particle physics may reveal whether nature permits such ingredients in usable amounts. Laboratory experiments already demonstrate quantum effects, such as the Casimir force, which create negative energies on small scales. Could future technologies magnify these effects, creating conditions that mimic the exotic requirements of a wormhole? A third frontier lies in quantum information science. Increasingly, physicists are discovering that spacetime and information may be two sides of the same coin. The ER equals EPR conjecture, linking entanglement with wormholes, suggests that progress in understanding quantum information may directly illuminate the physics of spacetime itself. Quantum computers, still in their infancy, could one day simulate spacetimes with wormholes, providing insights unreachable by pen and paper. There is also the frontier of imagination. As history shows, science advances not only by data but by daring questions. Kip Thorne's work on traversable wormholes began with a student's question. The future of wormhole research may be sparked by curiosity just as audacious, by minds willing to explore the improbable in pursuit of the possible. And perhaps the most important frontier is patience. Wormholes may not reveal themselves tomorrow or in 100 years, but neither did black holes. Once considered mathematical oddities, they are now observed routinely, their shadows photographed, their collisions heard across billions of light years. Wormholes may follow the same path, from speculation to certainty, given time and persistence. Every wormhole story is also our story. The future of wormhole research is not just about physics, but about what kind of beings we are. Do we accept the distances of the cosmos as final? Or do we insist on searching for hidden connections, on believing that nature may offer more than we yet see? The act of looking itself defines us, reminding us that curiosity is as much a part of the universe as gravity and light. And so, the future of wormhole research is not a single path, but a web. Astrophysics, quantum theory, quantum information, imagination, and patience, all intertwined. Each path may fail, or all may succeed. But the pursuit is itself a triumph, for it teaches us to look beyond the horizon, to expect wonder where we once assumed limits. As we close this chapter, we look ahead not only to the science, but to the imagination it inspires. For wormholes are not only a question of physics, but of humanity's drive to connect, to explore, to transcend. And so, our journey continues, from the laboratories of tomorrow to the deepest corners of imagination, where wormholes live not only as equations, but as symbols of our endless curiosity. This next part, wormholes and human imagination. If science is the careful measurement of what is, imagination is the reaching toward what might be. And few ideas have stirred human imagination as much as wormholes. They are the bridges of storytellers, the shortcuts of dreamers, the cosmic doors that open onto adventure and mystery. Even when the equations are daunting, the vision is simple, a tunnel that lets us go further than ever before. From the first whispers of Einstein-Rosen bridges, writers seized upon the concept. Science fiction transformed wormholes into stargates, hyperspace jumps, and portals across galaxies. In novels, they became the means by which civilizations spread across the stars. On screen, they shimmered as glowing rings, swirling vortices, or subtle folds in reality. Each depiction was shaped by its time, a reflection not only of scientific possibility but of cultural longing. For in imagining wormholes, we imagine freedom from the greatest limit we know, distance. The stars, beautiful but remote, call to us. A wormhole promises to bring them within reach. This is why wormholes resonate beyond the halls of physics departments. They speak to a universal human desire, to connect, to explore, to reunite with the distant. But wormholes are more than symbols of exploration. They also embody our fascination with mystery. To step through a wormhole is to step into the unknown. What lies on the other side? Another star system? Another universe? A different time altogether? In every depiction there is the thrill of possibility, the suggestion that the cosmos is stranger and richer than our imaginations can grasp. Science, too, benefits from this imaginative engagement. For Kip Thorne, it was a student's question that sparked the exploration of traversable wormholes. The collaboration between physicists and filmmakers on Interstellar brought new attention to relativistic physics and the challenges of wormhole stability. Even when artistic visions stretch the science, they ignite curiosity, and curiosity is the seed of discovery. Wormholes in imagination are also mirrors of human emotion. They appear in stories of love separated by light years, of journeys home across impossible divides, of quests that transcend barriers. They give narrative form to longing, to hope, to the refusal to accept finality. In this way, wormholes are not only physics but poetry, not only equations but metaphors for the deepest parts of the human condition. And perhaps this is their greatest gift. Wormholes remind us that science is not a dry pursuit, but a human one. Our equations are attempts to describe reality, but our imaginations are what compel us to seek those descriptions. The vision of a shortcut through space-time is a way of saying, the universe may yet surprise us, and we are eager for that surprise. Of course, imagination and reality are not always aligned. The physics of wormholes requires exotic matter and stability conditions that may never exist. Real wormholes, if they exist at all, may be tiny, unstable, or inaccessible. But that does not diminish their imaginative power. Even if wormholes remain forever theoretical, they will continue to inspire. And that inspiration is not idle. It shapes careers, motivates experiments, and keeps alive the sense of wonder that makes science thrive. For science needs more than facts. It needs dreams. Dreams remind us why the facts matter, why the pursuit is worth it. Wormholes, real or imagined, are part of that dreamscape. Every wormhole story is also our story. In the bridges we imagine, we see our own desire to connect, across the cosmos, across time, across the boundaries of the known. Whether wormholes exist or not, the act of imagining them is itself a triumph, proof that the human spirit refuses to be confined by distance or doubt. So, as we close this chapter, we step back from equations and experiments and return to the realm of wonder. The wormhole, after all, is not only a mathematical solution, it is a metaphor for hope, for exploration, for possibility. And it is imagination, as much as observation, that will carry us into the next horizons of discovery. This next part, limitations and boundaries. Every great dream is eventually met by reality. For wormholes, that reality comes in the form of limits. Limits set not by imagination, but by the laws of physics as we understand them. To contemplate wormholes is to walk a fine line between possibility and impossibility, to peer into the cosmos with both wonder and caution. The first limit is matter itself. Traversable wormholes, as theory describes them, require exotic matter, material with negative energy density. Ordinary matter obeys the rules of positive energy and attractive gravity. Exotic matter would do the opposite, holding the wormhole open by pushing outward against collapse. But whether such matter exists in usable quantities is an open question. The Casimir effect shows us tiny amounts of negative energy in quantum systems, but not enough to build a bridge through space-time. Without exotic matter, the equations collapse. The second limit is stability. Even if exotic matter could be found, wormholes may be inherently unstable. The slightest disturbance might cause them to snap shut before anything, or anyone, could pass through. Quantum fluctuations, tidal forces, and the relentless pull of gravity could all conspire to destroy a wormhole almost as soon as it formed. Stability remains one of the greatest barriers between theory and practice. The third limit is causality. If wormholes allow travel not just through space but also through time, then paradoxes loom. Can an event cause itself? Can a traveller erase their own past? These puzzles suggest that wormholes may be forbidden, not by energy conditions or engineering challenges, but by the logic of the universe itself. Some physicists, like Stephen Hawking, have proposed a chronology protection conjecture, an idea that nature will always prevent paradoxes by collapsing wormholes before they can be abused for time travel. Another boundary is observation. For all our telescopes, detectors and equations, no evidence of a wormhole has ever been found. We see black holes, neutron stars and galaxies colliding, but no signs of shortcuts in space-time. The silence of the cosmos may itself be a limit, telling us that wormholes, if they exist, are rare, hidden, or too small to ever notice. Yet these limits are not reasons for despair. They are reminders of how science works. To dream is essential, but so too is to test, to calculate, to confront reality. In doing so, we refine our understanding, sharpen our questions, and learn where imagination meets truth. And there is beauty in the limits themselves. For even if wormholes cannot be traversed, their mathematics still teaches us about relativity and quantum mechanics. Their paradoxes force us to confront the mysteries of time and causality. Their demands for exotic matter stretch our understanding of the quantum vacuum. Even if wormholes remain beyond reach, they leave us richer for having pursued them. Every wormhole story is also our story, and part of our story is knowing where we cannot yet go. To accept limits is not to give up, but to see clearly. It is to acknowledge that the universe is not ours to shape as we please, but ours to learn from, piece by piece, with patience and humility. Still, within every boundary lies a spark. The impossible today can become the ordinary tomorrow. Once, heavier than air flight seemed absurd. Once, black holes were dismissed as curiosities. Once, gravitational waves were too faint to ever be detected. And now we listen to them routinely, echoes of distant collisions ringing through our detectors. Perhaps wormholes will follow a similar path, moving from speculation to certainty, or perhaps they will remain forever out of reach. But whether real or not, wormholes fulfill a profound role. They remind us that the universe is not just a place of laws and limits, but also of possibility and wonder. To imagine them is to stretch beyond what we know, to test the edges of the possible, to explore the dialogue between curiosity and constraint. So we end this chapter with a paradox of our own. Wormholes may be impossible, and yet they are invaluable, for they show us not only the shape of the cosmos, but the shape of our own imagination. This next part, conclusion, the road's not yet travelled. We began our journey with a question. Might the universe allow shortcuts through space and time? Along the way, we explored Einstein's equations, exotic matter, quantum entanglement, and the paradoxes of causality. We imagined wormholes as both scientific constructs and symbols of our deepest longings. And now we arrive at the end of our path, or perhaps only a pause, for in science every ending is also a beginning. The truth is, we do not know if wormholes exist. They remain hidden, if they are there at all, woven into the fabric of space-time beyond the reach of our telescopes. They may be forbidden by the laws of physics, collapsing before any traveller can step through. Or they may be real but subtle, waiting for technologies we have not yet built, waiting for minds not yet born to uncover them. But even if wormholes are forever out of reach, the journey of asking about them has value, for they sharpen our understanding of relativity and quantum theory. They force us to think about causality, about time, about the nature of connection itself. They reveal where our knowledge ends and where wonder begins. And perhaps that is the greatest gift of wormholes. They remind us that the universe is not exhausted by what we know. The equations point beyond themselves to possibilities that stretch our imagination. Science is not only about answers, it is also about questions, and wormholes are questions given shape. Every wormhole's story is also our story. We too long for shortcuts across distance and time. We too seek connection where separation seems absolute. When we imagine a tunnel linking distant stars, we're really imagining a bridge between ourselves and the unknown. In that sense, wormholes are as human as they are cosmic. Metaphors of hope, symbols of our refusal to accept final boundaries. And as we stand beneath the stars tonight, it is worth remembering that the universe has already given us wonders we once thought impossible. Black holes, gravitational waves, the cosmic web, all were once speculation. Now they are part of our measured reality. Wormholes may join them, or they may remain dreams. But to dream of them is itself an act of discovery, for it shows us who we are, curious, restless, unwilling to be confined by what we already know. Perhaps one day, far in the future, our descendants will find a wormhole and step through, leaving our familiar cosmos for another. Or perhaps they will look back at our time, at our questions, and marvel at how we dreamed before we knew. Either way, the story continues. A story not just of wormholes, but of humanity's endless pursuit of understanding. And so we close this journey, not with certainty, but with wonder. Not with final answers, but with the recognition that science is an unfolding adventure. The roads not yet travelled may be wormholes, or they may be discoveries we cannot yet imagine. But what matters is that we will keep travelling, keep asking, keep looking beyond the horizon. If this story has inspired you, a like and a subscribe helps us keep exploring together, so we can continue telling these tales of the cosmos and wonder about the mysteries still waiting. Look up at the night sky, see the stars scattered across the darkness. Between them lies distance, yes, vast, unyielding, humbling. But in your imagination, there are bridges. In your mind, you can step across. And in your heart, you carry the most important truth of all. The universe is not a closed book. Its pages are still turning. Its mysteries are still unfolding. And you, Stardust Come Alive, are part of that story. The roads not yet travelled are out there, waiting. And perhaps somewhere beyond the horizon of our knowledge, a wormhole awaits.